In previous lessons, we learned several different ways in which we can describe both continuous and categorical variables. We also learned some basic methods for describing the relationship between two variables. In this video, we take the process of describing these relationships one step further. We will use SAS to construct 95% confidence intervals around our estimates. Recall the lecture on descriptive analysis, where we compared the average heights of men and women using a previous semester's class survey data. Or when we compared the proportion of people who reported various levels of general health within levels of having a personal doctor. In both of these examples, we can see differences in the values of one variable across levels of another variable. For example, the average weight for males is higher than the average weight for females, or that among the 15 people with one personal doctor, most, 80%, report that they're in excellent or very good general health. But how confident are we in these conclusions, and to whom do they apply? Well, we can apply these conclusions to our sample for sure. In other words, as long as we're willing to assume that everyone knows their weight and gave us an honest answer on the survey, then we're virtually 100% certain that the true average weight of men in our sample is 165.5 pounds, and the true average weight of women in our sample is 139.6 pounds. Therefore, we're also certain that, on average, weight truly differs by gender in our sample. But what about the entire class? How certain are we that this conclusion applies to it? Well, almost everyone in the class completed the survey, so there's very little chance that knowing the weight of a couple additional people would drastically alter our conclusions. Therefore, we remain relatively sure that the average weight of men and average weight of women in the class is truly different. But what about UNTHSC? What about the United States as a whole? As you can see, as we try to apply the conclusions we drew about our study sample to larger and larger populations, we begin to view the fit of those conclusions with greater skepticism. At the same time, more often than not, an estimate for the population mean or proportion is really what our interest is, and the sample mean or proportion is just our best approximation. So, how can we quantify how good of an approximation our sample mean or proportion is? One way we can begin to address this problem is with 95% confidence intervals. That is, rather than using our sample data to generate an exact estimate for height, we use our sample data to generate a range of heights that is likely to include the true average height in the population. And here's how the basic idea works. When we have a random sample of individuals from a population where the variable we're analyzing is normally distributed, then in repeated sampling, we can expect 95% of the confidence intervals to include the true population parameter. Remember that most of the time, the 95% confidence intervals include the true population mean when assumptions are met. Therefore, one quick way of eyeballing differences between groups is to check whether or not the 95% confidence intervals overlap. If they don't overlap, then we're pretty sure that the true population means are different. For example, when we plot the 95% confidence interval for female height, and we plot the 95% confidence interval for male height, we see that they don't overlap. And that provides evidence that males and females really do have different heights in the population from which our sample was taken. Before going any further, let's take a look at some simulated data to bolster your intuition about what 95% confidence intervals really mean. Our first example is just a proc means exactly like the ones you've seen many times. In fact, I just copied and pasted this proc step from our descriptive analysis lecture. But here I'm including the CLM option, which stands for confidence limits. The default is 95% confidence limits, which is what you will almost always use, but you should be aware that this can be changed. The estimated mean height for females, also called our point estimate, is 64 inches. The lower limit for the 95% confidence interval of this point estimate is 63.5 inches, and the upper limit of the 95% confidence interval of this point estimate is 65.1 inches. Before we interpret this confidence interval, let's do a quick simulation exercise. This code is not code that you need to be able to write yourself. This code is just for me to use to demonstrate a point. In this first part of the code, all we're doing is creating a variable called male and randomly assigning values of 0 and 1 to the variable. As you can see, we generated 10,000 total observations, and they're approximately equally divided between males and females. Next, we'll randomly assign heights to the males and females we just generated, This code tells SAS to assign heights in such a way that the average height for males will be approximately 71 inches, with a standard deviation of 4.32 inches, and the average height for women will be approximately 64.3 inches, with a standard deviation of 2.11 inches. Let's run it and take a look. As you can see, the data set now consists of two variables, male and height. When we run procmeans, you can see that the average heights and standard deviations are very close to those that we entered in our previous SAS code. And when we plot histograms of the data, we can see that the variable height is almost perfectly normally distributed. Now we're going to randomly choose samples of 100 people from our population of 10,000 people, and we're going to do that 1,000 times. Then below, we can calculate the mean and 95% confidence interval for males and females, and we're going to do this calculation separately for each of the 1,000 samples we just drew from the population and output those results to a new data set. As you can see, for each sample it shows us the number of observations drawn at random, the mean height, and the lower and upper confidence limits for males and females. For example, in random sample 1, 42 females and 58 males were selected at random. The mean height of the females selected was 64.5 inches, and the 95% confidence interval for that estimate spans from 63.9 inches to 65.1 inches. The mean height of males in the sample is 70.5 inches, and the confidence interval spans from 69.2 inches to 71.8 inches. In our case, because this is simulated data, we know the population means for females and males. As a reminder, the true population mean height for females was 64.3 inches, and the true population mean height for males was 71 inches. Looking at sample number 1, we can see that the mean heights estimated by this sample are not identical to the true mean heights of the population, but the 95% confidence intervals do include the true mean heights for the population. So, if we had done a real study and the simulated population we created was a real population, and we had drawn this study sample, our 95% confidence intervals would have included the true heights of the population we were interested in. But can the same be said for every sample we drew? This code just tags every sample where the confidence interval includes 64.3 inches for females and 71 inches for males. And as you can see, in approximately 95% of the samples we drew at random, the confidence interval did include the true population mean. In about 5%, it did not. So, if by chance we just happened to randomly draw one of the samples that did not include our population mean for our study, we may have reached flawed conclusions about the population. The good news is that, as you can see here, when assumptions are met, and if we sample many times from the population, 95% of the time our confidence interval will include the true population parameter. That's why some people say that the practical interpretation is that we're 95% confident that any single 95% confidence interval contains the population mean. Now going back to our original procmeans, we could interpret the 95% confidence interval in the following way. Assuming that our sample was drawn at random from a population in which height is approximately normally distributed, we're 95% confident that these intervals contain the true population mean. Of course, in this case, we haven't defined what our population is, so this sentence doesn't really make much sense. I suppose we could say that this is a sample of all public health students at UNTHSC. Now you practice calculating 95% confidence intervals. We often want to compare differences between groups at the population level. Are men, on average, more likely to get heart disease than women? Are people with lower incomes more likely to smoke, on average, than people with high incomes? Are older people, on average, more likely to have depression than younger people? Or in this case, are men, on average, taller than women? Confidence limits are one way to get a feel for whether or not our findings apply beyond our sample. In the remainder of this module, you'll learn how to use SAS to formally test hypotheses about population differences in means and proportions.